बाउंड्रीज बता दें
बाउंड्रीज अब तो नीचे तक आ रहा पूरा
ये आ रहा है
हैं और
आउटपुट में यूट्यूब का आउटपुट सो वॉल हो या यूट्यूब वाला स्ट्रीमिंग ओके सो गुड इवनिंग स्टूडेंट्स today I take up the laws of thermodynamics. Before that, in the thermal physics we did temperature, how to measure temperature and what is temperature. And one basic law in temperature was the zeroth law of thermodynamics. So the zeroth law of thermodynamics was what it was, ki heat, if objects A and B are in thermal equilibrium and objects B and C are separately in thermal equilibrium, then objects A and C will be in thermal equilibrium. So that was one of the most basic and fundamental law in thermodynamics, right? Then see, after that we did the how to make the different kind of temperature scales. Then we did in one more class of thermal physics, we did the calorimetry. Now it is about the laws of thermodynamics. Laws of thermodynamics. So see, in the laws of thermodynamics we have how these laws came into existence. You see, the fact is what, in whole of the physics, whenever you'll get to know about a new form of energy, the law of the form of law of conservation of energy will change. Like see, in the mechanics you did what? You had the potential energy, you had the kinetic energy, and there the law of conservation of energy was what? Law of conservation of energy was that sum of the potential energy plus kinetic energy will remain constant when it was a falling object or it was related to in all these kind of events. Like suppose there was a block and that struck a spring got compressed. In that case also the kinetic energy got converted into potential energy. So in those cases the potential energy plus kinetic energy was conserved and there was no other form of energy there. So that was the law of conservation of energy. Then you see, in the Bernoulli's theorem you got to know that the energy was there in the form of what? Pressure also. We call that pressure energy. In the Bernoulli's theorem you saw that when there was some gas in the container, that gas was filled with some pressure. So due to that pressure also the gas had some energy. We saw the use of that energy there. So because the pressure also has energy, means what? There became three form of energy in the Bernoulli theorem. One was the potential energy, the other was the kinetic energy, then was the pressure energy. So basically you can understand the fact that how another law of conservation of energy, that was the Bernoulli's theorem, how that would have been discovered. When in the process they saw that potential energy plus kinetic energy both are increasing. So from here the energy is coming. Then this form of energy, the pressure energy, was identified, that the pressure was decreasing and the decrease of pressure energy was resulting in the form of kinetic energy and the potential energy. Now here also see what happens. We know one form, like suppose we have a container. In the container we have a gas and there is a piston also, tightly fitted piston which can move, but the gas cannot leak out of the container and the air from outside cannot go into the container. Now see what kind of experiment we did. We gave some heat from the bottom of the container. So heat is a form of energy that you know. Heat jo hai, it's a form of energy that you know. So the heat supplied to the gas, some energy was supplied to the gas, and it was found that gas did some mechanical work. How gas did some mechanical work? The piston got displaced, because see the heat that you supplied, due to that heat the pressure of the gas increased. That pressure applied some force on the piston, and due to that force the piston moved. So force into displacement was the mechanical work done. But one thing surprisingly was noticeable there, that the amount of energy that we supplied in the form of heat, the amount of energy that we supplied in the form of heat and the work that was done, they were not equal. That means there is some lapse of energy. So where has gone that energy? So where is that energy? So for that, a new form of energy in the gaseous, in fact that is true for the solids and liquids also in fact. So the new form of energy was discovered there, and that was what? That was the internal energy. That is what? Internal energy. Means what? Due to their state. Due to their state means a gas is at what temperature? A solid is at what temperature? A liquid is at what temperature? Due to that state, the solid, liquid or gases, they have some energy in themselves. They have some energy in themselves. So I tell you about the very basic things about that energy, internal energy. So basically see, that is what was happening there. If the heat supplied, the energy that was supplied in the form of heat, if all of that was not getting converted into work, so where had gone the energy? The remaining energy was, that remaining energy remained with the system in the form of its internal energy. The internal energy of the system increased by the same amount, by the amount by which work was not converted into heat. Suppose you had 100 joules of work, you had 100 joules of heat, and the work done was suppose 80 joules. So where had gone that 20 joules energy? That 20 joules was stored in the system in the form of internal energy, means amount of internal energy of the system increased by that 20 joules. So this new form of energy was generated. Now you may think about that, what is basically the internal energy? What is the form of internal energy? See, like when I tell you about the heat, you can realize heat is a form of energy. And I need not to tell you that how it is a form of energy. You probably realize that heat is a form of energy. And how is heat, that you know. About the work, you got to realize in the mechanics. You could understand that if a force works on a body and the body gets displaced, the work is said to be done, and that work is also a form of energy. You know. Now what is internal energy? So internal energy of any substance, whether it's liquids or it's gas, it will be present in the form of what? It will be present in the form of potential energy. It will be formed in the form of potential energy and kinetic energy. Potential energy and kinetic energy. Now see, what kind of potential energy? You need to elaborate your definition of potential energy now. Otherwise, see, when it comes potential energy, the very first thing that comes into your mind is what? It is, there is a block. There is a block, and you carry the block upwards to a certain height, and you feel that potential energy has increased. Is that clear? Maybe now some of the students must have got that point also in mind, that when a spring is compressed or the spring is elongated from its natural length, then also there is some potential energy in the spring. Maybe till now that point would have come into the mind of some students, that it's not only that when a block is carried at some height, it has potential energy. When the spring is compressed or the spring is elongated from its natural length, then also it has got the potential energy. But see, what is the basic form of potential energy? It is this, see, whenever there is some internal force in the system, whenever there is some internal force in the system and you do work against that internal force, the work that you do is stored in the system in the form of potential energy. Like see, how I tell you about mgh. I tell you about mgh, then I'll tell you about half kx square also, then I'll get back to this point. You see, I told you that when there is some internal force in the system and when you do some work against that internal force, the work done is stored in the system in the form of its potential energy. Look at this. This is a block of mass m, and The system is what? System is block and the earth. They make one system. Block and the earth, they make one system. So the attractive gravitational force on the block towards the earth is an internal force, because I told you earth and the block, they make one system. So because see, the earth and the block, they are making one system. So that attractive force is what? It's an internal force, because that is an internal force. Now when you pull the block upwards, you are doing some work against that internal force. Internal force on the block was downwards. Why I'm calling it internal force? Because I told you that earth and the block, they make one system. So when the earth and the block, they make one system, then the attractive force between them is an internal force. When we pull it upwards, we are applying the force against the internal force. So we are doing work against the external force, internal force. And that work is stored in the system in the form of its potential energy. Now see, the same thing in case of spring also. Spring is a part of the system. Basically, spring is the system. So when spring is the system, what you do when you compress the spring itself generates a force in the outward direction. What you're doing, you are pressing the spring, so you are applying force opposite to the internal force, and you are doing some work against that. That work is stored in the spring in the form of potential energy. When you elongate the spring from its natural length, spring exerts a force in the inward direction. Spring exerts a force in the inward direction, and you're pulling it against that force. So you're doing some work, and that work is stored in the system in the form of its potential energy. So what you have to understand for the potential energy, basically the generalized form of potential energy is what? In a system when there is some internal force, and you are doing work against the internal force. You're doing work against the external force. In the work that you are doing against the external force, the force against which you are doing the work must not be a dissipative force. Must not be a dissipative force. Dissipative force what? Like friction. Friction is a dissipative force. That must not be a force like dissipative force. Dissipative force, I told you, like friction. So when you do work against the friction, that work is not stored in the system, it is converted into heat. So means what? There is an internal force in the system. When you do work against the system, against that internal force, and the internal force is not a dissipative force, in that case, not a dissipative force, you can take it like a conservative force. It should be what? It should be a conservative force. So when you do work against that conservative force, which is the internal force, the work is stored in the system in the form of potential energy. So this is the basic form of potential energy. So how is the potential energy stored in the substances, liquid, gases, and the solids? Because see, the substances have the molecules or the atoms. They are made up of molecules and atoms. And molecules and atoms, they have some attractive force between them. There is the internal force of the system. They have some attractive force between them. So because there is some attractive force between them, when you expand it, we do work against this internal force. When we try to compress it, we do work against that compressive force. The force of compression will generate some force in the outward direction, and we are doing some work against that. So that work will be stored in the system in the form of potential. That is the potential energy. So that means in the potential energy part, which is the internal energy of the substances, solids, liquids, and gases, we can say what? We can say that which potential energy will make the internal energy? The potential energy is stored between the molecules due to their interactive force. Due to their interactive force, some energy will be stored in them, and that potential energy makes the internal energy. So you see, I make one more point clear here. When we talk about ideal gas, you must be knowing about the ideal gas, that in the ideal gas there is no interactive force between the molecules. In ideal gas, there is no interactive force between the molecules. That means what? That means no potential energy will be stored in the ideal gas. So that means no potential energy. That means in the ideal gas, generally our discussion will be limited to the ideal gas. In very specific cases, we'll talk about the internal energy of the solids, liquids, or of non-ideal gas. Most of the time in the thermodynamics, when we'll discuss the laws of thermodynamics, our discussion will be related to the ideal gas. So in the ideal gas, you have to remember that there is no potential energy between the molecules. That means internal energy will be only due to what? Only due to the kinetic energy. Is that clear? And also make it clear here that suppose you have a container filled with a gas, then if the gas is non-ideal, gas is not ideal, in that case, there is some interactive potential between the molecules. Now, if you carry that container to the second or third floor of the building, the molecules had some interaction with the earth also. So the potentiality of whole of the system increases. Suppose the mass of the gas was 10 kg and you are carrying it up to height h. So potentiality of those molecules increases by mgh. But this potential energy will not contribute to the internal energy. This will not contribute to the internal energy because what I told you, the interactive energy between the molecules of that system, I told you, due to their interactive force. That means there is a force of interaction between the molecules, and due to that force of interaction, what is the potential energy in the system? That is a part of the internal energy. But if the molecules have some interaction with the outside agency like Earth, Earth is not a part of that gaseous system, because Earth is not a part of the gaseous system, or I'm talking about a block. Then the molecules of the block, they have some interactive force between them. Due to that, there is some potential energy. But if the molecules of the block or the molecules of the gas have some interaction with the earth, and due to that there is some potential in the system, that potential energy will not contribute to the internal energy. Now I talk about the kinetic energy. You see, in a liquid, gas or solids, especially in gases, you know that fact that when gas is filled in a container, what happens that molecules move randomly. Molecules move randomly. Due to this random motion is very much in gases and slightly less in liquids and almost nil, very small in case of solids. In solids, you know very well that molecules cannot move randomly like that, but molecules keep vibrating about their positions. Molecules keep vibrating about their positions. So vibration is also a kind of motion. Vibration is also kind of motion. So kinetic energy which contributes to the internal energy is what? It is the kinetic energy due to random motion of the molecules. Due to the random motion of the molecules, be it solid. So vibration is also a kind of random motion. This motion is also a random motion. If a molecule rotate about another molecule, that is also a random motion. So the kinetic energy due to the random motion of the molecules, that contributes to the internal energy. What does not contribute to the internal energy? Suppose there is a container in which you have a gas. Molecules of the gas are in a random motion. The kinetic energy due to this random motion will contribute to the internal energy. What will not contribute? If you keep that container on a train, and train is running with a speed of 100 km/h. So all the molecules inside the container, they are also moving with a velocity of 100 km/h. They are also moving with a velocity of what? 100 km/h. So because see, this is not the random motion of the molecules. All the molecules are moving in the same direction with the same velocity. And this kinetic energy of the gas will not contribute to the internal energy. So I make it more clear. Kinetic energy due to the random motion जहाँ लिखा है, you can write that what? Relative random motion. Here you can write relative random motion. Relative random motion means what? You see, this molecule is vibrating about this molecule. So this is what? Relative motion between the two molecules. This molecule is moving like this. So this motion is what? This motion is related to some other molecule which is also moving like this. See. But when all the molecules, when the container is kept in a train and train is moving with velocity of 100 km per hour, all the molecules are going in that direction with the velocity of 100 km per hour. So there is no relative motion between them due to that motion. So that will not contribute to the internal energy. So I hope that you could understand that what kind of potential energy, what kind of kinetic energy contributes for the internal energy of the material. But because our discussion will be mostly for the ideal gases. In the ideal gases, you just remember that there is no potential energy part. So the internal energy will be only because of what? It will be only because of the kinetic energy, and in the kinetic energy due to the relative random motion of the molecules. Is that clear? This is the internal energy. So when we keep a gas in a container, in a closed container, and there is a piston on its upper side, we supply the heat. Heat supplied is energy that increases the pressure inside the container, that applies some force on the piston. Piston moves upwards, so the work is done. Work is done. So some part of the heat supplied, some part of the energy supplied does the work, that gets converted into the work. In some part increases its internal energy of the molecules, that does not appear in the form of what? Work. And our discussion in thermodynamics, the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics will primarily be focused towards what? The prime objective will be to make a heat engine. That will be to make a heat engine. Like heat will be supplied, a part of that will be converted into work, some part will not be converted into work. So how much part is not getting into the work, that will calculate, and why it is not getting into the work, that will discuss, and also how can we make the process efficient. Because see, the target is only the thermal physics. Basically this part of the physics deals with what? This deals with the conversion of heat into work and vice versa. Conversion of heat into work and vice versa. Is that clear? So for this conversion, we need to know some more basic things about the gases. We will have to make some laws, by the laws by which all these things are governed. So now see, I tell you about the first law of thermodynamics. First law of thermodynamics. So the first thing about this is what? It's a form of law of conservation of energy. It's another form of law of conservation of energy. Is that clear? It's another form of law of conservation of energy. This is the first thing. Now see how we generated the law. It was like this. See, this is a PV diagram, pressure P, volume V. We have a system, we have a gaseous system in the state 1. Gaseous system in the state 1. How a state in the thermodynamics is defined? A state means, a state in the thermodynamics means what? It's pressure, volume and temperature. There are other parameters also, but basically these three things describe the state of a system. So the system was in the state 1, that means there was some value of pressure, there was some value of volume, there was some value of temperature. Now we carry the system from state 1 to the state 2 through some path. Path 1 we carry to the state 2. So when I talk about state 2, in the state 2, the pressure, volume and temperature, all the three or any of the two would have changed. You see, maybe the three parameters, all the three parameters change, maybe only the two parameters change, or at least the one parameter changes, then we'll say that the state has changed. And how the change of state can be brought in a thermodynamic system? The thermodynamic state can be brought to a thermodynamic state can be changed by what? We supply some heat delta Q1 to the system. We supplied some heat delta Q1 to the system, and in the process system did what? System did delta W1 work. System did what? Delta W1 work. And it was being carried through some operation, through some process. When you ask me, so what is the meaning of thermodynamic process? Thermodynamic process means under what law that change is being carried on. Under what law that change is being carried on means what? Listen it carefully. Suppose you have a system P1, V1, T1. You have gas at P1, V1, T1. Now we perform a thermodynamic operation called isothermal process. So in the isothermal process, pressure and volume will change, temperature will keep constant. We are reaching to the second state while we are keeping what? Temperature constant, and pressure, volume are being changed. This is one way of reaching to the other state. Is that clear? Or I tell you one more thing. Suppose you want to increase temperature of something. You want to increase temperature of something. There are two ways available. What? One way, you can keep the pressure constant and you can increase the temperature, or you can make the pressure variable and keep the temperature can keep the volume constant and increase the temperature. Ultimately the state will be changed, and there are two ways to carry on that change. What? That objective was to change the temperature. The processes available were what? Keep the pressure constant and let the volume change, or keep the volume constant and let the pressure change. Is that clear? So to one process you call the process of constant pressure, and the other process, constant pressure process, is called the isobaric process. And when you keep the volume constant, you call that isochoric process. These are the processes. That means what? When you change the state, during the change of state, you have to change it under certain law. You are keeping the volume constant, or you are keeping the pressure constant, or you are applying some other condition. You might be knowing about adiabatic condition. Adiabatic conditions are what? When some changes are brought in a system only by doing work, or only by getting the work done from the system, and the heat flow is restricted to the system, or from the system to the outside world. We call that process as what? Adiabatic process. Maybe you have done that in the chemistry. So if you have not yet done, still there is no problem about that. The point is that whenever the state is changed, state is always changed under a certain law. Maybe you are keeping the pressure constant, we are keeping the temperature constant, or there are so many other parameters also. You can keep one of the condition and you can bring that change of state. So this is one process. There's one process that I have marked. I have not told you what kind of process is that, but there's one process. In this process, delta Q1 heat is given to the system, and delta W1 work is derived from the system. System does delta W1 work. Now we carry the system from state 1 to the state 2 through another process. Means the process, other process means the law of reaching from this point to this point has changed through some other process. And in this process, we are giving delta Q1, delta Q2 heat to the system, and system is giving out delta W2 work. Similarly, in another process, we are giving, this is process 3. This another process means the law under which you are changing it, that's a different law. And in this law, what we do in this process, we supply heat delta Q3 to the system, and system does work delta W3. System does how much work? It does work delta W3. This is another process. Is that clear? What we find in all these processes, you see, state 1 is a unique process, unique state, means here the pressure, volume and temperature has got some value. State 2 is a different state but a unique state. Here also the pressure, volume and temperature have got some value. So when you reach from state 1 to the state 2 through the different processes, process 1, process 2, process 3, the amount of heat that was supplied, delta Q1, delta Q2, delta Q3, was different. Amount of work that was done by the system, delta W1, delta W2, delta W3, that was also different. But what we found constant was delta Q1 minus delta W1 was equal to delta Q2 minus delta W2, and this was equal to delta Q3 minus delta W3. I write it again properly. You see, what we found, delta Q1 minus delta W1 was equal to delta Q2 minus delta W2 was equal to delta Q3 minus delta W3. It was constant. Whatever process you do, but when you reach from state 1 to the state 2 in all the cases is same, state 1 in all the cases is same, in all the processes same. In that case, what we found that delta Q1 minus delta W1 is same. Now, what is the meaning of delta Q minus delta W? I told you just few minutes back. What? When we supply delta Q heat to the system, suppose 100 joules, system does delta W1 work, say 100 joules. So delta Q minus delta W, what happens to that 20 joules? It increases the internal energy of the system. And internal energy of the system is defined only by its state. Only by its state. Is defined by what? It's defined only by its state. Means what? What is the value of pressure, volume and temperature here? Internal will be defined only by that, not by how that state has been achieved. Suppose you got water at 40 degrees centigrade in a beaker. Then through whatever process you brought, initial water was say at 20 degrees centigrade, you heated by some means. By what means you did heat that, it does not matter. When the water in container 1, in container 2, in container 3, they are at 40 degrees centigrade and their amount is also equal, then their internal energy will be equal. It does not depend upon the fact that in what way the water in the container 1, in the container 2 or in the container 3 was heated. It was heated by gas, it was heated by Bunsen burner, or it was heated by some other means. It does not depend upon that. Is that clear? So, because in all the cases we are carrying from same state to the other same state, so delta U will be what? Same. And this difference is what? This difference is defined as delta U, and this is the first law of thermodynamics. This is what delta U, the change of internal energy. Means in any process, whatever heat you give to the system, and system does some work, the difference of that will be stored in the system in the form of what? That will increase its internal energy of the system. Or this law you can write in the differential form. I generalize this law now. This becomes dq minus dw is equal to what? du. This is the first law of thermodynamics. Is that clear? It is in the differential form. Is that clear? Or in the other form it can be written as what? Delta q equals to delta w plus delta u. So you see, though mostly the law is used in this form or in this form. Mostly the law is used in this form, but this form of the law is more descriptive. How? The heat that you give to the system, a part of that heat gets converted into work, and the other part is stored in the system in the form of its potential energy. So that you have to keep in mind now when we study the thermodynamics, that what happens, the heat that we supply to a system. And one more thing I would like to tell you here, look at this. When I said that internal energy of the system is defined only by its state, as I told you, mostly we are talking about what? Ideal gases. So in the ideal gases, internal energy is only by what? Because of its kinetic energy. in ideal gases, internal energy is only because of what? Because of its kinetic energy. And kinetic energy depends only upon temperature. It depends only upon temperature. That means in an ideal gas, when you change the temperature, we'll say that internal energy has been changed. When you don't change the temperature, even if you change the pressure and volume, the internal energy is not changed. That means you carry on a system, you carry on a process, and the state is changed from 1 to 2, but the temperature remains same. Like in an isothermal process, temperature does not change. So when temperature does not change, the delta U part will be what? It will be 0. We are talking about ideal gases. So in ideal gases, when delta U is 0, temperature does not change, because in the ideal gases, kinetic energy is only due to the kinetic energy is only makes the internal energy. There is no potential energy part, and kinetic energy of a gas depends only upon its temperature, does not depend upon the pressure and volume. So when there is no change in the temperature, like in an isothermal process, there is no change in the temperature, delta U change of internal energy will also be 0. That means in that case, delta Q will be equal to what? Delta W. That means in the isothermal process, what amount of heat you supply, all that heat gets converted into the work. Now, due to this statement, don't just think about the fact that, okay, so whenever we make an engine, we'll always select the process to be isothermal. Because the engine is never, any heat engine never depends upon one process. It's always a cycle. It's always not cycle. Because see, what you cannot do, suppose you have a container. In the container you have some gas. It's tightly fitted piston. Now from one side you are supplying the heat, and the pressure is generated. Due to that pressure, the force acts on the piston, and the piston moves along this direction. So the work is being done. Now you keep on supplying the heat, piston strikes to the gear, and gear starts moving. Is that clear? So what you cannot do it in one process, like you are supplying the heat, piston keeps moving along this direction, because there is a limit to the length of the piston. So in the engines, it's always a cycle. Cycle means what? In one stroke we supply some heat. That heat gets converted into the work. Then in the next stroke what happens? Again the gas gets compressed. Again the piston moves back to the original position. Again we supply the heat. The pressure is generated. Due to that pressure, work is again done. So it happens like this, see. And the piston, the rod connected to the piston strikes the gear. That strikes the gear, and the gear keeps moving in that way. So this is how the heat energy gets converted into what? That gets converted into the kinetic energy. So it's always a cycle. So when there is a cycle, if you say, okay, both the process in the cycle could be isothermal. If both the process in the cycle are isothermal, so in one process you are supplying heat that gets converted into what? Work. And in the reverse cycle, all that work again gets converted into what? Heat. So your work done ultimately is what? 0. You don't want that. So that means through the isothermal process, maybe you are getting the work, but when you get back to the original point, there are some other processes involved. So that makes the process inefficient. That is why we can never make any engine which is 100% efficient. So it's not that it has not yet been made, and in future it can be made. It cannot be made in the future also. There are proper reasons for that, why the 100% conversion of heat into the work is not possible. So now see, there is the first law of thermodynamics. So in the explanatory form, what you can say? You can say that heat supplied to whatever heat is supplied to a gas, a part of it does the work, and the remaining part gets converted into what? Internal energy. This is the statement of first law of thermodynamics. Is that clear? So you could understand that it is another form of law of conservation of energy. Now see, the terms that I have used here, the internal energy, I told you in brief right now. Now in more detail, I tell you about the internal energy. You see, these are the parameters that you will have to remember. I make here a chart. You see, it's like this. See, this for the internal energy, and this for the monatomic gas, diatomic gas, and triatomic gas. This is degree of freedom. This is about degree of freedom. What is the meaning of degree of freedom? I described you just now. This is translational. This is rotational. This is vibrational, and this is total. ये दिखाई दे रहा, ये end वाला. This total. This is what total. So let me tell you first of all that what is the meaning of degree of freedom. You see, when we deal with the gases system are what kind of a system? They consist of large number of molecules. Usually, if you think that the behavior of gas is the behavior of a single molecule, no, not that. A single molecule does not make a gas. A single molecule does not have a pressure. A single molecule does not have a volume. Temperature of a single molecule is not defined. What we define is the temperature of a gas, pressure of a gas, and volume of a gas. So gas, you can think like what? You can think of it is made up of large number of particles. So the properties of the gas or the behavior of the gas will be the properties of the compilation of large number of particles. Is that clear? And here we are not talking about the chemical properties of the molecules. We are just talking about what? For us in physics, the gas only means the compilation of large number of particles. And whenever that large number of particles will be there, it will certainly comprise of some volume, it will certainly have some pressure, and certainly it will have temperature. So see, I tell you about the temperature. Suppose you have vacuum somewhere, or say in this room we have some temperature, in this room we have some molecules, and in this room we have some temperature. Now what makes the temperature? What makes the temperature of this room? Definitely the molecules. If I remove all the molecules from the room, if I generate here the perfect vacuum, there is no molecule, the temperature of the room will become what? 0 Kelvin. Temperature of the room will become 0 Kelvin. That means what? The kinetic energy of the molecules, that counts for the heat part of the system, and that makes the temperature of this room. Is that clear? Now see, we are talking about large number of particles, so properties of the gases will be the properties of large number of particles. Now, how the particles can move? One particle may move in a straight line like this for the timing. Maybe after that it will strike to one molecule, then it will rebound and will go in some other direction. But before that, it can do what? It can move in a straight line. This is what? It's translational motion. When molecule is moving like this, molecule can rotate also. Molecule can move in a straight line while it's rotating also. It's rotating and it's moving. That is what? Rotational kinetic energy. Is that clear? And what if the molecule is made up of two atoms? What can happen? The whole of the molecule is moving while the atoms are vibrating also. And this can happen in that way that the molecule is translating. Altogether, molecule is rotating also. It's translating, rotating, and you see the atoms are vibrating also. While it is happening, this going, it's rotating, and the atoms are vibrating also, like this. It may happen in that way. So there is translational motion, and all this is relative. When a molecule rotates, it rotates related to what? It rotates related to the one atom rotates related to the other atom. Is that clear? One molecule translates with respect to another molecule. One atom vibrates with respect to other atom. One molecule translates with respect to one molecule translates with respect to other molecule. One molecule may rotate about some axis in which it is rotating about another molecule. So I'm talking about relative motion because I told you that only the relative arbitrary motion, relative random motion of the gaseous molecule make the internal energy of the system. But see, because it's all about the large number of particles, so through the Maxwell-Boltzmann statistics, for the gathering of large number of molecules, what we concluded that this translation motion is 1 degree of freedom. If it can rotate, it is 1 degree of freedom. If it can vibrate, it is 1 degree of freedom. And we concluded that 1 degree of freedom contributes for the half kT energy. It doesn't depend upon that whether it is translational or it is rotational or it is vibrational. Each degree of freedom, once again try to understand first of all degree of freedom, then I'll get back to the half kT. Suppose I start moving here in this way. This is 1 degree of freedom. What I do, I shake my hands like this, there's another degree of freedom. Now what I do, I move and I also shake my hands like this. Is that clear? This is what, now I have 2 degree of freedom. And when it is for what? It is for a compilation of large number of molecules. Then through the statistics, it was concluded that on average means what? Maybe in one molecule, the energy due to the translational motion is more, due to the rotational motion is less. In another molecule in the same gas, maybe the rotational energy was more and the translational energy was less. So when it is about the large number of molecules, sample of large number of molecules, on average, it was found that the total energy due to the vibration, due to the rotation and due to the translation was what? All same. So we related that to the temperature that 1 degree of freedom contributes to half kT energy, where K is Boltzmann constant. This is the Boltzmann constant, and you might be knowing Boltzmann constant K equals what? R by N naught. R is the gas constant and N naught is the Avogadro number. R is the gas constant, N naught is the Avogadro number. So Boltzmann constant K equals what? R by N naught. T is the temperature in Kelvin. And this law is called the law of equipartition of energy, which you can note down. The law of equipartition of energy says what? That each degree of freedom contributes equally to the energy, to the internal energy, and contribution of 1 degree of freedom being equal to half kT. I repeat that. The law of equipartition of energy says that each degree of freedom contributes equally to the internal energy, and contribution of 1 degree of freedom is equal to what? Half kT. Is that clear? This is clear now? So this becomes, now what we have noticed is that in monatomic gases there are 3 translational degrees of freedom. There are 3 translational degrees of freedom, because see, when molecule move related to the other molecule, its velocity, one component of velocity could be in the x direction, one component in the y direction, one component will be in the z direction. It is about the velocity of a molecule with respect to other molecule in the gaseous system, because the molecule is moving randomly, velocity component could be in the x, y, z. So this is what 3 translational degree of freedom. And because see, in the monatomic gas molecules, if I say that one molecule is rotating about the other molecule, it is not possible because the position of this molecule is not fixed. So how can it rotate about the other molecule? And if the molecule itself rotates, molecules are very tiny. Moment of inertia of the molecule about an axis that passes through itself, because that's a particle. So when the axis, whether it's along x-axis, along y-axis or along z-axis, but because that passes through the molecule itself, because the molecule is rotating about its own axis, and molecule is rotating about its own axis, and axis passes through the molecule itself. Molecule is very tiny, so all the mass is lying on the axis, so its moment of inertia is what? 0. Because its moment of inertia is 0, so half I omega square will be 0. So a monatomic gas molecule has no rotational degree of freedom, it's 0. The vibrational degree of freedom is also 0, because how? Because the position of one atom is not fixed with respect to the other atom. If you say that one molecule, it's monatomic, so one molecule is vibrating about this, but this molecule goes away from here. So about this molecule, it cannot be the vibration. It cannot be the vibration, so that means what? There is no vibrational degree of freedom. So in all total, there are 3 translational degrees of freedom, 3 plus 0 plus 0, so that is what? It's 3. Is that clear? Now see about the diatomic gas. But generally you have to remember it. Generally what? You have to remember it. Is that clear? About the diatomic gas, in the diatomic gas there are 3 degrees of freedom. Suppose you have oxygen. In the oxygen there are 2 atoms. Whole of the molecule which is having 2 atoms may move translationally with respect to other molecule along any arbitrary direction, where it has one component of velocity in the x, other component in the y, and the other component along what? Z. So it is a 3 translational degree of freedom and 2 rotational degree of freedom. How 2 rotational degree of freedom? Say this is a molecule. There is one atom and this is another atom. And the axis passes through both the atoms. Say this is the x-axis, it passes through both the atoms. If it rotates about that axis, moment of inertia I is what? 0, because both the molecules are lying on the axis itself. But see, if y-axis passes from here through one of the molecule, y-axis passes through one of the atom, then the mass of the other atom is away from the axis. So it has got, if it rotates about this axis, in that case it has got some moment of inertia I. Also, if it rotates about the z-axis and the z-axis passes through one of the atom, in that case also the other atom is away from it, it has got some moment of inertia about that. So about the x-axis, say, which was passing through both the atoms, its moment of inertia I was 0. So even if it was rotating about that axis while it was translating, still there is no rotational kinetic energy because of that. So about the z-axis and y-axis, it has got rotational kinetic energy, so there are 2 rotational degrees of freedom. And vibrational degree of freedom, there are 2, but write a star sign here, conditions applied. Usually in most of the calculations, in 99.99% calculations, we won't consider this vibrational degree of freedom, because vibration of the molecules, vibration of the atoms in a molecule start usually at very high temperature. When there are 2 atoms of oxygen, unless the temperature is very high, the atoms will not be vibrating. The atoms will be vibrating only at what? Only at relatively very high temperature. So unless examiner tells you that vibrational degree of freedom is to be considered, usually I have not seen a question in which vibrational degree of freedom has been considered in the calculations. But when there are some different kind of results, what different kind of results I'll discuss later on. When there are some different kind of results and we calculate the internal energy of the gas, and that internal energy of the gas does not cannot be calculated by only counting the translational degree of freedom, only by counting the rotational degree of freedom, then the objective question could be what could be the reason for it. And in those cases the answer had been, okay, the vibrational degree of freedom had been started at that temperature, so that is why the total amount of energy is not coming to be, when we calculated it from the what the total internal energy is, that is not coming to be equal to what we calculated from this degree of freedom and this degree of freedom. Is that clear? So this is under this what conditions applied. What condition? It is only when temperature is very, very high. Temperature is very, very high. So total we'll write here what 5. We won't consider this. Similarly here also. Here we have translational degree of freedom 3, whole of the molecule can move along x, y or z direction, and this also here 3. Why it is 3? Because see, even if x axis is along the 2 atoms. It's along what 2 atoms? And obviously I'm talking here about what? Not a linear molecule in which all the 3 atoms are along the same line. It's not about that. It's about a triangular molecule in which all the 3 atoms are not along one line. So in that case what happens? That even if 2 atoms are lying along the x-axis, the mass of the other atom is away from the axis. So even if atom rotates about the x-axis, there is some moment of inertia and there will be some energy. So in this case the total translation energy will be what? 3, and this total energy, if we consider it, it will be what? It will be 3. So this will be what? This will be 3. There are 3 pairs of molecules for the vibration. There are 3 pairs, so there will be 3 because there are 3, I'm sorry, it's 6. Because there are 3 pairs and 1 pair of vibration makes what? 2 degree of vibration, degree of freedom. So this is what? 6. So the total becomes what? 6. 3 plus 3, we won't consider this. This is about the degree of freedom. And as I told you in the law of equipartition of energy that 1 degree of freedom contributes for the half kT energy, internal energy. 1 degree of freedom contributes for the half kT internal energy. That means now you know each and everything about the internal energy. If I tell you about that, this is the kinetic energy of, this is the internal energy of one molecule due to 1 degree of freedom. So now if I tell you about I tell you the temperature of the gas, I tell you the name of the gas, and I tell you the amount of the gas, you can directly calculate that what is the internal energy. How? Suppose we have oxygen, 4 moles of oxygen at 300 Kelvin. Now we need to find what is the internal energy. Let's calculate. Because see, in the oxygen is a diatomic gas. Look at the table. Diatomic gas has 5 degree of freedom. So 3 plus 2, 5. 3 translational, 2 rotational. That becomes 5 degree of freedom. So because there are 5 degrees of freedom, so due to 5 degrees of freedom, one molecule will have half kT into 5, this much of energy. It's because of what? Of one molecule. So of 1 mole, it will be this much. Because 1 mole consists of n naught number of molecules. So this is of 1 mole, and there are 4 moles, so into 4. Is that clear? Into what? 4. So this is the total internal energy of that sample of gas, which is oxygen, has 4 moles and is at temperature what? 300 Kelvin. We can keep the temperature here, and K is what? When you keep the value of K is what? R by N naught. So N naught into N naught will be cancelled, and the answer will come only in terms of what? R. Is that clear? R is the gas constant. So this is how you can calculate the internal energy of an ideal gas. And you need to calculate the internal energy only for what? Only for the ideal gases. So this is all about the internal energy of the gas. Now see, the next parameter in the laws of thermodynamics is what? It is the work delta W. I'm telling you about all these 3 parameters of the first law of thermodynamics. One was delta U, the other is what? Delta W. So now see, delta W, we will always write it delta W, never W. You may notice before that, you may note few more things about the internal energy. Internal energy. One thing that it's a state function. Means it depends only upon the state, upon nothing else. And in that state also is what? Temperature, because we're talking about ideal gas. So it depends only upon the state function. It's a state function. Second, what? It's not a transient function. It's not a transient function. It's not a transient function means what? It's like that you have a gas in a container. If someone asks you what is the internal energy of a gas, it is defined. Means what? This function internal energy is not defined only when system is in transition. Like when system is in transition, its state is being changed. If it is defined only during the time when state is changed, then we call it a transient function. But because see, when there is a gas in a container and there is no transition in the system is kept as such, still the internal energy of the gas is defined, so it's not a transient function. And third, it is not a it is a state function. It's not a transient function, and it does not depend upon the process. Means when you carry from one state to the other state, through what state you are carrying it, it does not depend upon that. It only depends upon what is the state. So these three things are noticeable about the internal energy. Now you'll see. Now the second, delta W. So first of all, delta W, it's never W, it's always delta W, the work function. Work. It's always delta W. It's always delta W means what? It's a first thing, it's a state function. It's a transient function. It's a transient function. It's a transient function means what? Suppose there is a container in which there is a gas and you're not doing anything with the system is in equilibrium. Then because no process is happening, volume is not increasing, volume is not decreasing, no work will be done. Because volume is not increasing or volume is not decreasing, that means piston will not be moving. That means no work is being done. And work is not defined there. Work is defined only when piston moves. That means when volume changes, when system is in transition. So delta W will be defined only for what? When system is in transition. So it is what? It's a transient function. Secondly, it is what? It's a path function. Path means what? Process. Path means what? Process. Means what? It's a path function. Suppose you are heating something, you are giving some heat to something, and temperature can be increased in two ways, either at constant volume or at constant pressure. So see, in both the cases the work done will be different. Means the same target is being achieved. You're reaching from one temperature to the other temperature in both the process. In one process you are keeping the temperature volume constant, in the other process you are keeping the pressure constant or the volume constant. And what happens? And what happens is that the processes are different, the work done will be different. So what depends upon that, in what way you are reaching from one state to the other state, work depends upon that. It does not depend upon the state. Is that clear? It does not depend upon the state. Is that clear? Achha, one more thing. In the first law of thermodynamics, delta U is positive when it increases. When internal energy of a system increases, it's positive. And delta U is negative when internal energy of a system, when it decreases. If internal energy decreases, delta U is negative. If internal energy increases, delta U is positive. And here for the work, the fourth thing is what? For the work, the fourth thing is that delta W is positive if work is done by the system. If work is done by the system. If work is done by the system, the delta W is positive. Is that clear? By the system, it is positive. And when it is done, when volume increases, whenever volume of the system increases, we say that the work is being done by the system, and that work is what? This work is positive. Is that it? That work is what? That work is positive. So I'll tell you more about the work, etc. So this is the end of today's class, and I'll discuss next time further about it. So in the next class, I'll definitely be able to complete the work part, the delta Q part, and I'll be able to complete that much of part by which you can do the questions related to the first law of thermodynamics.